Let's see. Why don't we do... Oh, shoot. Real quick. This guy. Just in case you're curious. This is basically log base 2 of something equals 1, right? So you would do 2 to the first power equals this, right? So it'll be 2 to the first power equals log base 3 of 4x minus 2. Right? If this was an x in here, log base 2 of x equals 1. How would you solve this? 2 to the first is x. Done. But it really doesn't matter what's in here. You do the same step I just did. Log base 2 of anything equals 1 is 2 equals that anything. So log base 2 of stuff is 1. 2 to the first equals stuff. Now what do I do with this? Same thing. So 3 squared equals 4x minus 2. You get 9 is 4x minus 2. Add 2 divided by 4, you get x is 11 fourths. Cool. And does it work okay? It makes this positive, right? 11 fourths. 11 minus 2 is 9. Log base 3 of 9 is 2. So that's positive, thankfully. So log base 2 of 2 is 1. Yeah. Okay. So it's sort of like when you have multiple radicals. If I have 2 radicals in an equation, I've got to square it twice. I had 2 logs in this equation. I had to do that process twice to undo both. Okay.
Skip all that by just doing 4x minus 2 equals 9?
Oh yeah, if you could put the, because it was a 1, it made it easy to tell where it was going to go, right? Is that how you did it?
Yeah.
Yeah. Totally. So if you could see where that number is going to end up once you do both of the logs, sure, of course. All right, you're good now. Good. Let's try this. Let's do one of these guys that we already have in the right format. That's kind of gross. Let's do another one. But this guy, let's do this guy at least. X squared over 25 minus y squared over 1 equals 1. So that's the first one on that number 3. Now just a very quick, the way I did this one was I had an ellipse problem, and then I said this is basically kind of the opposite of that. It's related to sandwich versus stay away from me kind of idea that we saw earlier this semester. So let's do this. Let's do this. Stay with me for a second. Let's graph this, and then we'll graph the hyperbola. We'll do a minus. So this now that I've done that is, what is this?
Ellipse.
An ellipse, right? And how big can x get?
5.
It's got to stop at 5. If you put a 6 there, would this number be bigger or smaller than 1? If you put a 6 here. It's bigger than 1. It'd be 36 over 25. Bigger than 1. I got to add a positive thing and make it somehow become 1. That can't happen. I can't add a positive number to something already bigger than 1 and make it become 1. I have to subtract, right? All right. Maybe. I just want to break down why these numbers suddenly tell you how far to go in every direction. It's because they tell me how far my variable values are allowed to go. So x can only go out to, well, not only. Poor little y dude stuck even more. X can go up to 5 and down to negative 5. Now, and think about it. If x is 5 or negative 5, what is this? 5 squared, 25 divided by 25 is 1. So then what's y got to be so that it still equals 1? 0. Now, you got to engage the old brain. Come on. You got to engage the brain. If that's already 1, what do I add to it to make it become 1? Frickin' 0. So that's why these are here. The exact same reasoning applies to the y piece. How big can y get? You can only go 1 up and down. And if y is 1, then x has to be 0. So you have 0, 1, 0, negative 1. So you got this UFO kind of thing going on. That's not horrible. But it's nowhere near good, Jeff. Oh, too bad for me. Yes, sir.
So only x or y should be 1, right? Should equal to 1. Because how do we know? How do we know it's 5?
Because it's 25. And so that's like x over 5 squared, right?
Yeah.
So the biggest x could be to make this equal 1 is 5. Now, if x is smaller than 5, if x is 4 or 3, then y is going to be the part that it's missing. It's going to be what it's missing. Does that make sense?
Yeah.
If x is 4, this is 16 25ths. In fact, let's try this. If x is 4, stay with me for now. We're doing more work than we have to. See how we're done? See how we're done? But I really want to explore why it does what it does. If x is 4, then I have 16 25ths plus y squared equals 1. How do I solve for y? Oh, it's crazy. Subtract 16 25ths. What do you get there? Yeah, 9 25ths. I like it. So y equals now. Plus or minus, right? Is that cool? Everybody follow that? Do you have to do this? No, but I want to show you why it kind of starts at 0 and then it goes. Because the minute x is less than 5, y has to be more than 0, so it fills in to make it become 1. Do you really have to know all this to graph it? Obviously not, because we're done with the damn problem, right? But at 4 then, at 4, or negative 4 to be honest, wouldn't it be the same? At 4, this goes up to 3/5, and it goes down to negative 3/5. So at 4, what did we just figure out? If x is 4, what's y got to be?
Plus or minus
3/5 or negative 3/5? There. If x is 3, y is going to have to be a little bit bigger. If x is 2, y is going to have to be a little bit bigger. And if x is 0, y has got to be the biggest so that it's 1 itself. And then when you go back here, it just kind of repeats again now. Okay, I like it because of all the squares. You got all this symmetry because of all the squares. Again, did you have to know anything I just said after I plotted after I made this picture? No, you really didn't. I love that. And now somebody's going to say, yeah, he tells us all this useless shit. Damn. So what if this would have been a hyperbola? And let's just straight up make this a minus. But there's another associated hyperbola we can look at. So I like that. I think somebody pointed this out. This is sort of like a less than absolute value equation. Oh shit! Right? I don't know if you guys want me to do that, but it's like a stay close equation, absolute value equation. And now we're going to look at stay the hell away from me. So this is going to be on the outside of this. Is it going to be on the x or y axis? X-axis. So it's going to basically look like that. It's going to be like somebody cracked this open and turned it sideways. So how do I do that then? I sort of start as if I'm going to make the ellipse. So I still know this is 5. I still know this is 1. 5 on the x, 1 on the y. So I'm still going to put 1, 1, 1, 2, 3, 4, 5. 1, 5. I'm going to put something here. I'm going to put an open circle here because it's not really on the y-axis. It is on the x-axis. So I'm going to put close dots there. That's actual points on the graph. What do I do with those points? What does that help me create? Little rectangle. I like it. And then as a guide, to make sure that I get the right curvature, I draw these asymptotes through the corners. Hopefully you can do better than me. And now I can just kind of use them as a guide. And see how that kind of matches the curvature here, especially if I was drawing a little more precisely. So there's not a whole lot of work. There is a lot. There's like the equation of the asymptotes. The book talks about that. I'm not going to be overly worried about that, to be honest. If you go into pre-calculus, you're going to analyze this a little bit more. But for right now, I mean, it's really quick to get that sucker going. Please let that be quick. If you can do it for an ellipse, you just don't connect them. You make a rectangle instead, draw through the corners, bam! It's unbelievably quick. There's also, you can find out the focus and all this kind of business. That's all side noise for right now, to be honest. I don't know if you guys remember, what would the focus form would be here? Yeah, there's already a minus there, so this guy's got to have a plus. That's how I remember it. So the ellipse, the focus equation has a minus. Hyperbola, the focus equation has a plus. I'm sorry, I haven't finished that out yet. So this would be c squared equals 25 plus 1, 26. C is the square root of 26, which is a little bit bigger than 5. So the focus would be out there like it should be. Right? The whole thing. Now what would have been different if the equation would have been x squared over 25, y squared over 1 minus x squared over 25. So the y squared would have been positive. Yeah, all this work would have been valid, except now this would be the points, and it would go, and look at this, look how wide this sucker's going to be. Wow! All right, Jeff, that was unnecessary. Because think about it, if I cut this in half this way and turn it, isn't that what you expect to see? Because now, if I cut it this way, now it's going to be, that's exactly. If I cut it this way, I'm going to turn around. Whoa! No. If I cut it and turn it, wow. Okay, that's basically what's really happening. It's really nice. That's awesome. So whichever term is the positive one is the axis that the picture sits on. Which axis does this not touch? The x-axis. Because there can't be any x-intercepts, not any real ones. Thank God we're not graphing complex. Because holy shit, that would be hard. So we don't allow complex possibilities for right now. Okay.
With complex, do they interlap or do they
Oh
meet in the
man,
middle?
with complex, complex requires you to use color to represent depth because you don't have 4 dimensions to work in. That sentence, I don't know how much sense it made, but you just trust me. You don't. Yeah, basically have to use a computer almost to really do a good picture. If you look up fractals or graph of complex variables or something, you'll see very colorful graphs. Black on the graph is where it's the most complex. The lighter the color, the less complex it is. So that's how they show. Remember in the video I showed you when they picked it up? So it's not easy to do that on paper. So instead of picking it up, we just show the valleys. It's almost like a topographical thing. We show black is like deep and then, in a way. I don't know, that's enough. This class is not a complex variable analysis class. Oh, shit. But it's interesting. It really is interesting because it gives you the real complete picture. We're missing some stuff here, to be honest, but it works for most things. Circles hopefully should be relatively simple. So if I gave us, let's see, has everybody got what they want from this here? More than you ever wanted? So again, you might have to start off by completing the square. But if I had like x minus 5 squared plus y plus 3 squared equals 9, what can you tell me about this circle? The center is who? 11. So I'm going to make 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5, negative 3 is the center. And then the radius is 3, so I just, from that center, oh, my bad. Make sure you make this like, if you want to put something here, make it an open circle because it's not a part of the graph. It's the point that all the points on the graph are the same distance from. So that point is not on the graph. So where would I go from here?
3 up, 3 down.
Yeah, go up 3, 1, 2, 3. Down 3, 1, 2, 3. Over 3, 1, 2, 3. Over 3, 1, 2, 3. Cool. And then you make an approximation of a circular shape. Right. Make a little face as you want.
Aw.
No, I'm just trying to get any reaction out of you I can. So let a circle be easy. You should know how to complete the square. That should be one of the easier things that you've been asked to do in this class. Complete the square, see what ends up over there. If I'm going to ask you to graph it by hand, I'm going to kind of make sure that this comes out to be something not like 11. That would be kind of sucky. Go out, square root of 11. Okay. So obviously, if this is a negative number, you have more than likely done something wrong. Right? Okay. So that's a quick rundown of what we did in chapter 13. So let's get back. Any questions on any of the stuff we just did? Yes?
How can I find the length of the x-axis and y-axis?
For an ellipse.
Yeah.
So shoot. So remember earlier it was 25. So remember, what was this? This was related to going out 5 on the x in both directions. So how long will it end up being? 5 that way, 5 this way. So it's going to be
Alright.
10.
So if we have 25, the y will be 5, right?
X.
Oh, the x will be.
I did a fantastic job. Right. So in the x direction, I would go 5 in each direction. So of course it would end up being twice that. So on the handout, you see the 2a and the 2b.
Okay.
That's why it's doubled, because you go one way and the other way.
Alright.
So it'll be 10 length on the x-axis. It'll be 2 length on the y. And the easiest way to do it is just graph it and then just look at it. Right? Okay, maybe. Maybe not. Okay, well, we'll see. Anything else before we get into 14? The last chapter of the summer? Okay. So we talked really generally last time about certain types of sequences. I did a little preview of some stuff we're going to see. Let's get very, very, very detailed right now. So if I have I can define, let me do it like this. Let's start with the sequence we talked about before. Something like this sequence here. We didn't talk about this sequence, but still. What kind of sequence is this? What do I keep? What defines the next term? Add 3. I love it. What is the first term in the sequence?
2.
So I'm going to call that, what we call that is the first term, A1, is 2. It's just a standard practice to use A to denote the elements of the sequence. So what's A2?
5.
That's great. And so forth, right? A3. And really, what is this really? Let's break this down. I might as well do a little bit of a, getting ahead a little bit. How did I get to 5? I started at 2, and of course I did what you just told me. I added a 3. A3 is 8, which was start at 2, and add how many 3s? 2. Well, A4 is 11, which is start at 2 and add how many 3s? 3. So this was add 1 3, right? And this was add how many 3s? A1, you start at 2, and how many 3s do I add?
1.
That would get me here. How do I stay here?
0.
Yeah, add no 3s. All right. Do you guys see a pattern You see a pattern there. What is the number that keeps changing? Yeah, this piece here, it'll be what we call, actually we're going to use the letter N. This is what keeps changing here, right? You guys with me? So if N is 1, you get 2 plus 3 times 0. How does this number relate to this number? Always. Yeah, this is always one less, right? So what would AN be? The nth term. Well, to get to any term, I start at 2, and I add a certain number of 3's.
Which is
N minus 1. I love it. So really, a whole other way to think of this physically is, if I start at 2, how many steps do I take to get to the term I want? So if I want the first term, I don't take any freaking steps. I'm there, right? So if I want the first term, I take 1 minus 1, I take 0 steps. If I want the second term, I got to take 1 step. So 2 minus 1, that's the 1 step I got to take. So forth. So I look at this as steps that I'm taking to get to that term. So now if I ask you, what is the 88th term? Thank the gods you don't have to go, I'll get there. Okay. No, I can just do this. If I want the 88th term, how would you do that? Plug 88. What's A, 88? 2 plus 3 times 88 minus 1. 2 plus 3 times 87. 263, I think.
Yeah.
This is almost the most basic thing math does, is to find a pattern and capture it. It's one of the most basic things math does. So sequences are really just the fundamentals of math. Right now there's a search going on, and I was doing it for a while, but I just couldn't find it, to try to figure out if there's a pattern for prime numbers. I don't know if you guys know this, but they have computers running trying to find the next largest prime number. It's insane. Yeah. This is a big thing. So it's already been proven that the prime numbers never run out. What hasn't been proven is there a pattern to get from one prime number to the next to the next? Right? I know a lot of you guys are sitting there saying, what the shit good would that be? But you never know. You never know. And it's interesting, and you never know what good it's going to be until we have it, and we go, oh, we can use that for this. Oh, shit. Anyway. This is what's called an arithmetic sequence. Arithmetic. Because the nice thing is, it's based on addition, and this word starts with the letter A. You gotta love that shit. Okay. Doesn't quite work that way for the formula, for the sequence based on multiplication. We call those geometric, just, because. So geometric sequence would be something like this. What you got, Jeff? Let's go 2, 6, 18, 54. What's the idea here? Yeah. The first term is 2. Let's get really formal here. I got to back up and get formal here too. What's the common ratio? Which is a silly way to say it. What do I keep multiplying by? 3. And really, so isn't that 18 divided by 6 is 3? 54 divided by 18 is 3. That's why I call it a common ratio. So we use the letter R for it. Back here, real quick, back here, A1 was 2. What was the common difference? 3. Okay, I like it. So let's go back here. So A1 is 2, R2. So A1 is 2. A2 is what? A2 is 6. How do I get to 6 from 2? 2 times 3. A3 is 18. That would be 2 times 3 times 3. Right? I multiply. Every time I want to take another step, what do? Multiply by another 3. So to get to the second one, I multiply by 1, 3. To get to the third one, I multiply by 2 3s. To stay at the first one, I multiply by no 3s, right? Just stay there. I don't want to take any steps. Now you start to realize a very similar kind of feeling pattern to it, but it's based on multiplication. So what's an? It's going to be 2 times 3 to the n minus 1. Yeah. It kind of sucks. I wish they wouldn't do this. It kind of sucks that they start at a1. You could start at a0, and then you wouldn't need this n minus 1 shit, but oh well, too bad. They start at 1, so. And that's really why they give a letter n here, because it's related to natural numbers. 1, 2, 3, 4, 5, 6, right? Not whole numbers. Okay. Maybe. So that's geometric, looks like that. And arithmetic looks like that. So in general, the general form of this, what was 2? Why was that special for this? It was a1. What was 3? R. And then, of course, that's to the n minus 1. So that is the general form for any sequence based on multiplication. What about the general form for any sequence based on addition? It would be an equals, what was 2 again? A1. Plus 3, what was 3 here? D times n minus 1. So start somewhere and add so many of these. Start somewhere and multiply so many of these. So what I just did, just to catch you up, is I actually just did section 14.2, the beginning of it. Just because I wanted to. Section 14.1 is much more basic. We have a couple more things to do with this, but let me, before I leave 14.1 in the dust, and then we'll take a break, I think. 14.1 does stuff like this. What if I gave you a different sequence? These are not the only kind of sequences there are. So what if I said, here's the sequence, an equals 2 minus 5 over n. We're like, nice and gross. So what's a1?
2 minus 5 over 1.
Yeah, so what am I letting n be? I'm letting n be. So you see how this is not exactly looking like functional notation, but it still acts like it. The n is the variable. So a1 means replace n with 1. That's it. So it'll be 2 minus 5 over 1, 2 minus 5, negative 3. What would a2 be? 2 minus 5 over 2.
Negative 3 over 2.
Yeah, so that would be 4 over 2, right? Is it currently over 1, the LCD. 4 over 2 minus 5 over 2 is negative 1/2. Or you can think 2 minus 2.5 is negative 1.5. Negative 1/2, sorry. What would a3 be? 2 minus 5 over 3. Need the LCD. I mean, do you guys... So that is exactly acting like function notation. It just doesn't look the same exactly. But it's a sequence notation, but n is the variable. So if they say a7, you throw a 7 in where you see n. Wherever you see n. Just like if they said f7, f of 7. You replace the variable 7. It's the same idea. It's just we represent it differently because it's now we're talking about sequences. Cool. That's basically all 14.1 is. So let's take a break, come back. 5, 10, 20, 40 past. Come back 40 past.